So you had an exam how long ago?
That had been last Friday.
Oh, okay.
Yeah, it went really well.
Cool.
Like just I had a couple like small things that I did wrong. Like I was just kind of tossing them up. Like they weren't stuff I even came and saw you guys about because I thought I understood them pretty good. It was just like I think it was with the ionic. It wasn't net ionic. It was the other ionic equation. Like
Oh, the not oxidation stuff, but
no, not oxidation stuff. I have my exam. It
like
was
total ionic.
Total ionic.
Yeah.
Thank you.
Yeah.
And so like you had to have like each part broken up, and I forgot to like label it or something like that. Like I forgot to put like a charge.
Well,
or
there's some like our last organic chemistry quiz. Like for some reason, I remembered like how to rotate single bonds on question number 2, and then it was as if on question number 3 that information completely went out of my head. So like fortunately on this particular quiz, he like had the thing where you can write up why you got it wrong and then submit it back to him, and then he'll give you some points back. So I did that. But yeah, sometimes you forget to do stuff even though you knew it.
Yeah, it happens. All right, so this week
Lab stuff?
Yeah,
Okay.
we just got done doing. Well, we've done titrations before, but we did titrations with an antacid, like to find like, how much antacid is consumed. I'm trying to. So I understand like how to do this, but I'm not understanding. So like, the question is asking how much of the calcium carbonate is being used, or how much stomach acid is going to be neutralized. Not necessarily how much calcium carbonate is being produced. So that's what I'm kind of
Using your average. Oh, okay. Yeah, I remember this question from somebody else. So we're given moles because moles is what we already figured out. So we could have moles be the beginning of our train track, as it were.
okay.
And then we want it to end with a volume. So I'm guessing that we're going, like, to get from moles to moles, what are we going to use?
From moles to moles, we don't use grams. We use liters, right? Or no?
So anytime,
Like moles to moles.
anytime I want to get from moles of A to moles of B, what is the
you just do like a
thing?
mole ratio, right?
Yes, which I get from what?
From my balance equation.
Yes, that's what I was looking for.
Okay.
So that's how I'm going to do that.
How's it
I'm
go?
going to get from moles of the base to moles of the acid. And then what am I going to need to get from...
So moles of base to moles of acid. and
Or I
weight.
shouldn't have... I did this backwards, darn it. Okay, moles of base to moles of acid. There we go.
Yep.
So,
So we're going to go from moles of base to moles of acid, and then we're going to do, we're going to use moles of acid to find out what our molarity, no, not molarity. We're going to use our molarity because it gives us
there we go.
to find the amount that is neutralized.
Because I want to get from moles of acid to volume of acid. And to do that, I need some conversion factor that involves both moles and
liters.
And
So
that's
that-
molarity.
Molarity. Okay, so I'll go from. Okay, so I'm gonna go from 0.0058 moles of CaCO3 times.
And let's, I'm sure you balanced it right, but let me just...
Yeah, that's fine.
Or was this given to you?
I balanced it.
Oh, you had
so-
to figure this out.
Mhm.
Okay, so...
I just-
2 hydrogens, yes. 2 chlorines, 1 calcium, 1 carbonate, 1 carbonate. Yeah, okay.
Okay, and so I'll have that many, and then I have 2 moles of HCl per 0.1 mole So it's just gonna be 2 times point. It's gonna give me the amount of moles for my.
You can keep the train track going if you want to, though.
Okay. So.
I think. Sometimes I'm wrong when I say that, but I'm pretty sure you can
So
in this case.
moles, and then that'll cross out, and then it'll give me. I need to calculate this amount of moles, these amount of moles, right? Because I mean, if I keep the train tracks going, I would do.
Well, like,
That would be. Oh no, it would be.
because what molarity are you eventually going to use?
I'm eventually going to use 1.3
Yeah.
moles.
So, 0. Where's another?
Eraser?
No.
Or marker?
Here. So write out for me what that, like, write me that in another form, if you could. I'm trying to
It's-
ask the question in a vague way.
It's just going to
to
be
give it an idea.
0.137 moles over 1 liter.
Yes. So so that's the easiest transformation of it. The first transformation. So it's going to be moles of HCl
For 1 liter.
over liters of HCl.
Mhm.
So what is another transformation I can do to this?
Another way of writing that?
Yes. So another way that I could write this that it would be equally true, because this is the same thing as that. It's just
Yeah.
another way of writing it. So what's an even different way of writing this?
Like 1.73 moles divided by. I mean, that's the same. I mean,
Oh, like moving the decimal around? Is that what you mean?
or not 1.73. I meant
But, like-
points. But I mean, it's just. Like if you did, like I mean, you could move it around to have millimoles and milliliters.
I'm keeping the same units.
Yeah,
in the one
that's
that
like
I'm
it would make sense to me to do that.
Yeah,
so
so
that's
keep
why
the
I'm trying
same-
to understand where you're going.
So like
like mole. Okay, so like if you wrote 0.173 moles over 1 times 1 over 1 liter, like cross multiplying would be like technically.
but then we're making another conversion factor.
Yeah.
Yeah. So what where I'm going with this is that a conversion factor is basically a fraction that's like this. That
Mhm.
because this is why it's always valid to multiply by
Yeah.
1 because it equals 1. So you can always do this.
Yeah, they're equal to each other.
And so you can flip them and it's still valid. So what I
Okay.
want this to be is 1 liter of HCl, which is the end thing that I want.
Okay.
We said that. Divided by 0.137 moles of HCl. And then I have moles of HCl on the bottom.
On the bottom, okay.
We should get rid of that. Now, the way that you were going to do it is also perfectly valid. You could find the answer to this and then do this.
Yeah.
You could do that. But
Okay.
you'd have to do this eventually.
Yeah. Yeah. Okay. So do 1 liter over 0.137 moles of HCl equals volume, basically, right? So will equal my volume that I want, because my last conversion will be liters, and that'll be
Oh, 3.7.
3.7. Sorry,
So,
I wrote liter moles for some reason. Yeah, moles per liter. So that'd be it, right?
because we want
Because if we
liters of stomach
okay,
acid.
because if we took and did this and did it the way, we'd still.
Yeah, because let's pretend that we did it the way
I was
that you were
going
going to
through
do
it.
it. So what would we get out of this?
So we get. .0116, and then we'd take and we'd have .0116 times 0.137 moles.
Well, like
Or
that
no,
would be
no,
that would
that
be
would- that would-
.0116 what?
Oh, .0116 moles of HCl.
Moles of HCl.
Yeah.
So then to get from
So I'm gonna take, and I want to find liters, so I'm gonna take, and I'm gonna
0.0116 moles HCl.
Mhm.
So then what would let's forget that we wrote this here for a sec.
I want to finish with liters, so I'm gonna write it like 1 liter over
Yeah.
1 liter over 0.137 moles of HCl. Because I want to finish with liters either way. So I mean, it's just what I would have done over. I'm so used to going from milliliters of HCl to moles instead of moles to liters.
Oh.
Like,
yeah.
like doing the opposite, and like
Yeah.
I couldn't think about it how it would make sense for some reason.
Mhm.
Divided by 0.37 .08, so I'm gonna go to 3 sig figs. Sweet. Okay.
And I'm curious what you got for your percent error on the other page.
It was rough. It did not go so well.
Well, that's what I wanted to ask you about, because some people were making it out that they had got worse than they really did just by some of the ways they did the math.
I had 16.1%.
Okay, well that's not as one person thought they had gotten like 0 points or oh wait, percent error, percent yield. What did they use here?
Percent
They do
error.
percent error. So yeah, their percent error was just awful, and we went back and changed this one little thing.
Yeah, I think I did the math right. I just
Yeah. But 16.1 actually isn't. That's not bad for percent error.
Yeah.
Anything like what my physics professor told me is that like below 15 is good. So you're like
close to good.
borderline good actually. I don't know what it is. It varies a lot by experiment.
Yeah, and then, like, I think my last titration I had but we only did it twice, and so like I was pretty accurate like for the 2 times, and this we had to do it 3 different times, and like one of them one of these I think it might have been this one, which was what threw my average off because of 0.4. Like I made a mistake and then I rushed like doing the rest of the experiment because I had to restart it.
Oh,
I took
yeah.
and I started titrating without.
So that's why this one is so much different.
Yeah,
than,
I started titrating without an indicator. I didn't put my.
Been there, done that.
Yeah,
Yes.
so I
So
had to
you know you're
completely-
putting in base forever, and you're like, why isn't it turning pink?
Exactly.
Yeah.
And so I had to completely restart,
Yes.
and like
Done that.
I was already I was already one of the last ones going through, and I just
And
wasn't
then did
careful.
your professor have you like drop some phenolphthalein in there, and it turns like this dark crimson? And
No, I dropped it
just
in there
knew.
just because I wanted to see like how bad did I really do, and like just in case I didn't over titrate it, and I did. I very much so did. It was a very bright pink. It's like, okay, I get a restart now.
Hey.
Yeah, it wasn't.
Because the real thing is 0.5, right?
Yes.
Is like per tablet, so that's even like
Or
qualitative.
no, that's the average mass that I got. So percent error.
Yeah, but like the you get that by comparing it to an actual of 0.5. Right?
Yeah.
Yeah. So I mean, even qualitatively, I mean, that's still around half a gram.
Yeah. So I mean, it's not awful. It was like I said, I rushed it, so I know why I did bad. So this one, I think I understand what they're like. So they're asking if having water in the burette is going to make a difference. Like, so I know water doesn't make a difference necessarily in like down here if the water's being added to the Erlenmeyer flask, but if it's in the burette, it's going to throw your calculations off while you're titrating.
Okay.
And so if you have water, it's going to either give the illusion that you have more Well,
Yeah, because you're
it's going to give you the illusion that you have more base than you actually do have.
yeah, your base is going to be more dilute than you think it is.
Mm-hmm.
So for every volume of base you add, you're actually
Adding less than you
less
actually
than
are.
you think you are.
Yeah, and so then
Okay.
that's going to make it look like it's going to make it look like you've added more base than you've needed to, because it's not going to titrate.
So you're going to think that, for instance, there was.
Say.
Well, let's look at the specific question.
Yeah.
So, yeah, probably both. Because what we were just talking about is accuracy, basically,
Mhm.
that you wouldn't be like correctly reflecting reality.
Yeah.
But so why did
Accuracy-
you put precision?
So precision is like a constant result, and you're not going to have a constant result, because once you titrate it once you're going to be rinsing it out with titration, and then you'll have a more consistent. You'll slowly get a more consistent titrate.
So it won't even be wrong consistently.
Yeah.
Yeah.
Which makes sense to me.
So it's worse for both.
Mm-hmm.
Okay.
And then the accuracy will obviously be lower, because you're gonna have an inaccurate measurement to start out with that's going in your equation, and then that inaccurate measurement is going to affect how you calculate your mass, right?
Yeah. So we have to.
So I have to explain that it's going to cause an inaccurate measurement.
Yeah.
That
But
will
we have to think about
how it will be.
how,
Yeah.
and this is where
That's where I've
you
been.
can't do this too fast,
Yeah.
or you'll confuse yourself.
Yeah.
So
I was thinking about it both ways, because I was thinking about, like, it's going to make you bless you. It's going to make you misjudge where your measurement is, obviously. But like you said, it's going to dilute it, so like you're most likely going to be adding more, like.
well, because it goes back to like how we're calculating the mass of it in the
Yeah.
antacid. When I was explaining this to another person, I drew a picture of this. So let me see if
Okay.
I can pull that back up here. If not, I can see if I can draw it again.
I mean, I can kind of visualize it, like see something
Yeah,
in my
it's-
head. Like, I understand.
Well, it's not for your benefit; it's for mine. Because unless I
Fair
can,
enough.
I'll have to read the lab again really quick if I can't find the picture. Here it is. Okay. So. What it was, so correct me if I'm wrong, that you had this beaker, and you put an antacid tablet in there,
Mm-hmm.
and then you put some acid in here too, right?
Mm-hmm.
A certain amount of acid, of a known molarity.
Yes.
So known volume, known molarity. So you know exactly how many moles of acid you're putting in here.
Yes.
Okay. So those moles of acid is this red line. And then some of those are going to react with the calcium carbonate. That's what these blue lines are about. And then
Yes.
the other is the part that reacts with the NaOH that you put in.
Mm-hmm.
So what we're trying to find is what's left over of the acid after this reacts. So after moles of acid is depleted by the tablet, you're going to get some leftover acid, right?
Mm-hmm.
Okay. And this is what we measure. So
But I want to know what the mass of my tablet, like, of
Yeah.
the CaL3 from, like, I'll
From
find,
this
from the
calculation.
leftover.
So first you have to know, is your did not rinse his burette properly and residual water was left in there.
Mm-hmm.
So he has dilute base that he's putting in there, so how is that going to affect how much of this he thinks is in there?
That's going to gonna make him think that there is less of that. If you're adding more, titrant, more base to your acid from where you start, like so you start, and you're going to have to add more since it's diluted in order to, and so then when you added more, that's going to give you a larger number of milliliters. That's going to give you a larger number on top than it would. So he would think he would have more.
There we go. That's what I was looking for.
A definitive
Yes.
answer.
Well, no. You before you said that he would think he had less of
Less, yeah.
which it's easy to think that, but
Yeah.
then when you started talking yourself through it, then
I
you
had
have
to, I had
yeah,
to look
when
at
you
the
looked
actual
that.
equation
Yeah.
and realize that I'm going to be multiplying by, not dividing. Yeah.
Exactly. So, or another, like when I think of it is, I'm the person doing this and I go, oh my gosh, look at how much base I had to add to finally titrate this. There must be a ton of it in there.
Yeah.
But it's really just because my base was really weak. So, this is going to be higher than it should be. And that's where this
So that's going to be higher than it
picture
should
comes
be.
in. So this stays the same. This is reality. This red is reality. And this first, so say that this is the reality line between the yellow and the blue.
Okay.
Well, so if this gets bigger and we think that more of this acid was left over, then what does that do to the amount that we think was reacting with the calcium carbonate?
It's going to make that smaller.
Yes.
Because we're going to have more left over. So like less of the calcium carbonate is going to have reacted with the antacid or with the acid because we are thinking that we have more acid in the end. Or
Yes.
yeah, our
So
calculations
the
are going to show
because
that.
what we think happened is we go, okay, we're putting this base in there. Oh my word, look at all this base we had to put in there. There must have been a lot left over. That tablet must have barely done anything.
Yeah. Mm-hmm.
So that I think at least is the first part.
Yeah,
of that
that's going to
question.
be, so that's going to be the low, you're going to have a lower amount of calculated calcium carbonate.
Yes. And you can double check that, I guess, by I didn't think of that before, but yeah, looking at the math and seeing.
And that
if-
that makes sense because if you took and you had, this would be your number of moles that you would have calculated, and so that would have given you more moles, and you would have subtracted that from the amount that,
yeah. So you would get,
of a smaller amount of.
this would be bigger,
Mm-hmm.
and so this would end up being smaller.
Mm-hmm. Yeah, and so that difference that you find would be smaller, and then when you take and you do your mole ratio, you're going to have less moles of. Yeah, you'll have less
Carbonate.
moles of carbonate. Okay, that makes sense, and then I can explain my reasoning. Because, like, obviously water isn't going to affect the mass of that's actually in there, but it can affect, like, your math and how you show
Your perception.
your perception or your accuracy of your calculations.
Yep.
Okay, that makes sense now.
It's 2:14.
Okay, not bad. I have about an hour left. Good.
Where you have to go?
Menti meeting.
Oh, sure.
Yep.
A constant in the life of
Mhm.
a GSSE mentor.
No rest for the wicked.
But you don't have to describe yourself as that if you don't want to.
I was talking about my mentee. Okay. Okay, so explain your reasoning. So,
Your professor just makes them do like the lab, like the
Um,
week after, kind of?
Well, normally we do it like during the lab, but this one, since we were doing 3 titrations, she's like, you guys will probably run out of time like towards the end of the lab, so you can just bring the post lab in. But she's really cool about it. She's
Is
one
it
of
KO or?
no, she's one of the graduate students.
Oh, okay.
Or not graduate students, teachers assistants,
Oh.
TAs. Jessica Bloom, you might. I don't know if you know her, but.
It makes me happy when I see, like, one of the grad assistants for biology now is my friend Alexis, so it makes me
Okay.
laugh when she shows up in my blue.
That would make sense.
Good. Yes.
Yeah, that makes.
Yes. Because
Yeah.
I had to think about that one when I saw that question.
Yeah, that one made sense to me from what we've learned, but like that one, like it made sense that it would be higher. Like at first I'm like, oh, no effect, but I'm like, oh, it's in the Barrett, so that goes in your calculations. That makes sense to me. Because how you explain that?
Because would that be like something similar or different to what we did right here?
It'd be exactly the same.
Yeah, that's what I was
basically,
thinking.
Because you're going to calculate more acids since the whole entire antacid tablet wasn't
Yeah.
dissolved, and then.
Except that this time there really is more,
More
there.
acid, yeah.
Yeah,
Yeah.
that you're seeing.
But it's
for a
going to give
different
the
reason.
illusion that you're not
Yeah.
actually.
But still, this is here.
Mhm. Cool. That helps. Now I just have to do the pre-lab for tomorrow. So, and she doesn't
Okay.
actually take our pre-labs. Like
It's just helpful to
do
know what's
because
going
if
on.
I do that, then I'll do better on the lab quiz.
Yes.
So I'll probably work on that tonight. But I have a couple more questions about lecture.
Oh, okay.
If that's all right.
All right.
Nothing major, just like the last half basically of pressure. She kind of flew through it, and there's the pressure with something over or under the square root of something. I don't really remember it. I have my notes, but I know
Okay.
that doesn't explain it very well. Pressure of gas. So like, I understood like PV equals nRT like really well. Like I did really good on those we had on the exam.
Oh, okay. So this is something else.
Yeah. This is with. Oh, okay. So diffusion, maybe not pressure. Diffusion and fusion.
Oh.
That would
okay.
be different. That would be different than pressure. I just remember it with the notes on
Well,
pressure.
it's. I mean, it's still
It
a
has an
bunch of
in-
gas molecules
yeah.
flying around in the air. So.
It's kind of like an influence of pressure in a way.
Yeah,
if you think about it,
it's-
because like that's how molecules spread.
So let's take a look. Okay, so this mu RMS stuff that I am still. Another guy and I sat for like half an hour and figured this out once. So, I understood it then, so, but
So we know.
diffusion versus effusion. Okay, so what part of this made the least sense? And we'll start with or maybe we shouldn't start that way. So what part of it made the best sense, and we'll start there.
That's a good question. Because, like, I understand where she's getting, like, this. I'm not so sure I understand how this, like, sets up. But, I mean, it's just the equation you have, and so
Well,
you plug
it
in
helps
for
if
it.
you understand it, though. So, how this is derived. So, R is still the universal gas constant, so it's still
Mhm.
going to be 3 times, or I'm just doing units here.
0.0.
So it's going to be some constant times mole liters of, no, atmosphere liters over Kelvin moles.
Mhm.
Then that T is temperature, so that's going to cancel out your Kelvin. Then, I'm trying to remember what the M is. What do you plug in for M? When you plug in for M?
I want to say that was
Is that mass?
molar mass. That sounds right.
I want to say it's mass.
Yeah, because if you did it for helium, it'd be a molar mass of 4.08.
Water.
And yeah,
Or no,
this is-
H2.
that'd be
Yeah,
H2. So
Yeah,
that'd
so
be molar mass,
which is
of-
going to be in grams per mole.
Mhm.
Grams per mole, so that gets rid of
Moles.
moles. So then,
You'd be calculating for grams. Or no, you're still going to be calculating for your
you
rate.
must, R must be given in some other units here. Because this is speed. This is
Yeah.
it ends up being meters per second. So I'm
Meters per
trying to,
second.
let me go here and, so, units of R in, RMS equation. professor tell you what to make R when you're doing these equations, like what to paste in for R? Maybe that would be easier.
I thought it was just like your.
Is it the normal one?
I thought it was just the normal one for like. That's different.
Like with it, do you have an example of one of these that like your professor worked out the whole thing? Or since you said she flew through it, so maybe.
Yeah, that's why I was just like, I was at a loss when we went over it. So I believe it would have been just the normal like 0.08 to 06. So that would have been what you were doing.
Oh,
atmospheres
no,
per. Oh no, it's going to be
I
joules.
think it's, yeah, that's what.
Because
what
joules
it is.
aren't joules meter squared per second squared.
Yeah, that's what I was trying to remember. So it ends up being joules per mole Kelvin. Well, a joule is the same thing as.
Meter squared per second squared or something.
I don't know it off the top of my head. I just always look it up. I should have it memorized by now. I'm a senior science major, but.
Did you go over that with physics, right?
Yeah, I learned it in physics, but
Or
so
kilograms,
kilogram meters
meters
squared over
squared,
second
second
squared. So if this is a, and you have to, so kilogram meters squared over second squared, and then whenever you're doing this, you have to account for the fact that, does she talk about, or your lecture professor, I mean, talk about how you deal with the fact that this is in kilograms? Because some professors do talk about that explicitly and some of them don't.
I honestly don't remember much
Talking about the whole kilogram thing?
of anything from that's still not the right.
Because that's how you finally get the units to cancel, is that when you plug this in the denominator, you, no, it really doesn't look like your professor, maybe they modified R so that it's in grams instead. Like, because if this, where was that one for R? Where were the different ways? There they are. Okay. So if this is what it is in, so this is 8.3145 kilogram meters per second over second squared.
Multiply it
Over-
by 1,000.
Yeah, so you could just multiply this by 1,000 and then it would be fine. So your professor is probably just using a different R that has
Okay.
grams there. But anyway, I didn't mean to get all muddled here.
Well,
The
that's
grams and kilograms end up canceling if you do it right. So let's assume that your professor did that and just had grams there. And then you end up with just meter squared over second squared, the only thing left, and this is just a constant, so it has no units. You square root that, and you get meters per second. But, like next time you have class, it would be really good, like does your professor like allow for like 2 questions before a given class period? Sometimes?
Should probably be open. I'm not for sure.
No, or maybe office hours, I don't know. But to ask like specifically what she wants for each of these so that the units cancel. So that when you guys are doing math with this equation on tests, you can show your work correctly. But because then that also impacts, since this is kind of how they derive this too.
But I mean, we're not going to have to worry about these as being constants because we're just doing molar mass.
Yeah, you just do mass.
So that won't.
So,
be
oh yeah, you're right. So the difference between a fusion is just the difference. It's just a molar mass ratio type thing. Yeah, I kind of remember that, but for that, for
Yeah.
diffusion.
Yeah, I'll have to ask her. Hopefully that's not on the quiz, but I bet it'll probably be. So we'll see how that goes.
Well, she'll. have you been given R in the past with its
That's
units?
possible, yeah.
Yeah, so you would know what to do based on what units R has. So let's say she gives that R that she gave before where it's this, where it's kilograms, and you need to put something down here so that units are going to cancel. So your periodic table is going to give you grams per mole. How are you going to make that kilograms per mole so that it'll cancel this out?
You'd go. I was just gonna say you go to.
I should write this in train tracks so that it makes better
I
sense.
say because you can't go from. I was gonna say. 'Cause I was
It's
thinking-
actually not
I was
too
thinking
bad.
milligrams to millimoles, but you can't do that. So grams per mole. If you had 1,000 grams, you'd have 1,000 moles. Is that how you were?
You could do that. I'm thinking of a way where we don't have to change as much stuff. It's just one train track to fix this. So, like, pretend this wasn't here for a sec.
So trying to find, like, use the train track to get away from moles.
No, I want moles. I still
yeah,
want
'cause
it
you wanna
to.
know.
I want it to cancel moles. It's just this grams won't cancel this kilograms. So I
Mhm.
want to fix that. So how?
Multiply by 1,000.
Okay. So 1,000 what?
So 1,000 grams over 1 gram? No.
Is that a valid conversion factor?
No. Over 1 mole? Or 1 kilogram?
So now you have the conversion factor. There's just one thing wrong.
I have them upside down.
Yes. So if we flip that then, because this is what I assume your professor is
Because you'll
going
be
to do.
dividing by grams.
Yeah.
Not
So I assume what your professor is going to do is she's going to give you the normal R in joules per mole Kelvin and
We're
expect
gonna-
you
to convert.
this to kilograms per mole.
Yeah.
Because it's not too bad. Because all you do is do this, 1 kilogram over 1,000 kilograms, grams cancel grams. You end up, so say this,
Like point
this was
whatever.
your number, so you just end up with A divided by 1,000 as your number, and you have kilograms per mole, which is the units you wanted. So then, to do this in the cleaner way, so we start this, we have 3 times R, which is going to be in joules per mole Kelvin, times T,
Temperature.
which is just in Kelvin.
Mhm.
You may have to convert from Celsius, but whatever. Then we take that over kilograms per mole, which we derived from grams per mole from the periodic table.
Mhm.
And then we know that this is kilogram meters per second. So we cancel kilograms. This was kilogram meters squared over second squared. Kilograms cancels, moles cancel, kelvins cancel, and you just end up with meters per second. Because chemistry professors like you to show your units.
Mhm.